Hi, it's time for another math easy solution. Today we're going to discuss further into parametric curves, and now we'll go over example 1, which is this example right here, which says sketch and identify the curve defined by the parametric equations x equals t squared minus 2t and y equals t plus 1. Now, since both of these functions, x and y, are well, they're functions of t, we can go about graphing this is basically just set some points for t, and then see how the x and y's change, and then plot the x and y coordinates. Yeah, so here is the solution to it that I went over. Basically, here's a table of the values, and I'll show you the Excel sheet I made. Basically, each value of t gives a point on the curve as shown in the table, and curve below. So we pick, let's say for example, -2, -1, 0, etc. And then we get different values for x, and we can plot this out. And here I've plotted this out. So for example, I just picked values for t, so -2, -1, etc. And then if you click inside here, you can see this is just t squared minus 2t, etc., and we get all this over there. Then we can plot this over, and I'll put the link for this exact Excel sheet as well to download. And just to show you an example manually, basically, for example, we'll just pick a point. So for example, when, let's say, t is equal to 0, what we end up having is, well, x is equal to, notice it's t squared minus 2t. This is just going to be 0 squared minus 2 times 0. In other words, 0 minus 0 is going to be equal to 0. And then for the y, we have t plus 1, so this equals to 0 plus 1, so this equals to 1. So what we have here is a point, and this point is at 0 and 1. So x is 0, y is 1. And then when we graph it out here, this is when x is 0, y is 1. So that's this point right here. So that is at a 0 and 1. Yeah, and on this point of this is again an xy coordinate. At this point of the curve, this is when t is equal to 0 at this point. And then if we looked at over here, this is when we have x is 8 and then y is actually -1. So that is at t is equal to -2 here. It says t equals -2, and then at here we have 0 and looks like it's 3, so 0 and 3, or I mean 3 is x and 0 is y. That's at t is -1. So as you can see here, as you move through time, as you increase, this is going to be equal to 1, this is equal to 2, and so on. This is equal to 3, and then the last one, this is at about 8 and 5. That's about 5-ish here. This is at t is 4, like that. So this is how the curve looks like. And then again, a recall from when I went over the definitions on parametric curves and equations. And a good way of visualizing this is imagine a particle moving along the curve as it increases in time, as time passes. So basically, a particle's position is given by the parametric curves moves along the curve in the direction of the arrows as t increase, and I'll draw the arrows here. So basically, a particle would be moving across like this here. I'll just it's too small that, yeah. So it basically goes across like that, goes left and increases to the right side there. And also, what's interesting from this curve is notice that at consecutive points marked on the curve, so at t is -2, -1, etc., appear at equal time intervals. So everything here is separated by 1 second or whatever time it is. So basically, the difference here, delta t, is equal to 1. Every single one, -2, -1. So even though they're all separated by the same time intervals, but not equal distances. For example, this one here is separated by this much distance, but then here and here, for example, from this point to there is separated by a smaller distance. So, but the same time, the time is the exact same for both distances. So that's pretty interesting. And this is because the particle slows down and then speeds up as t increases. So that's a good way of visualizing it. So here it's going fast and it slows down and then starts increasing the speed. So that's one way of visualizing it if you're thinking about a particle moving along the curve. And now this curve appears to maybe be a parabola, and this is again from a part here we're asked to define, so identify the curve defined by it. So it looks like a parabola here. That's my guess. Yeah, and in fact, it is actually a parabola. If we can, so we can prove this by eliminating the parameter t, or the t parameter, from this. And again, this could be confirmed by it. And the way to do that is, well, let's just write this down here. So we have x squared, x equals to t squared minus 2t, and then we also have y is equal to t plus 1. I just want to check if I wrote this right. So yeah, t squared minus 2t and t plus 1. So if we try to eliminate the t parameter and try to make y as a function of x, what we get here is, well, we can change this. Yeah, rearrange this so we get t is equal to, just move the negative 1 on this side, so t is equal to y minus 1. And then if we bring this over inside here, and then put the t values inside here, what we end up getting is x is equal to t minus, this is y minus 1. Y minus 1 squared minus 2y minus 1, like that. Yeah, let's move that over here, there to make it clear. And also now we have this squared over there, the square y minus 1 squared, and we can expand that out. I'll do that separately here. This is the same thing as writing, and by using the FOIL method, it's the same thing as writing y minus 1 times y minus 1. So we multiply this and then add it to this over there. So we get y times y, which is y squared, and then y times negative 1, which is negative y. And then the same thing over here, we multiply this by this and add it to this by this. So we get a negative y there, negative 1 times y. Negative 1 times negative 1 is just plus 1. Negatives become a positive, so then this part equals 2y squared minus 2y plus 1. And you can do that in your head as well. I just wanted to do that for completeness sake. So now we have over here x is equal to y squared minus 2y plus 1. And then here we could multiply this 2 inside. Negative 2y, and then negative 2 times negative 1 is plus 2. So now what we get is this combines here. So this is going to be equal to y squared minus 2y adds up here, so 4y, and then the 1 and 2 add up to 3. So we have 4y plus 3, and this is what our x function is. So as you can see here, this is what we have, and this is in fact a parabola. This is a horizontal parabola actually, because we have x as a function of y in this case. Yeah, and you can learn more about parabolas in my earlier videos. I'll put a link below to that. But basically, yeah, so we can move around this and see that it is in fact a parabola. Yeah, so now a further note I want to make is that, well, in this example we did not restrict, or basically note that no restriction was placed on the parameter t in this example, so we assume that t could be any real number. But sometimes we restrict t to lie in a finite interval, and often the case is we want it to be a positive number, because t is usually representing time, so we don't want a negative value for t oftentimes. So for instance, in our example, consider the parametric curve x equals to t squared minus 2t, y equals t plus 1, but now we restrict t to be greater than or equal to 0 but less than or equal to 4. So this is the same thing as what we did, but now we ignore the parts where it was negative. So you can even go here and click here. Yeah, click here, and then let's just make it so that it's greater than 0, greater than or equal to 0. So if you restrict it, it goes something like that. So that's how the curve would look like, and you could copy and paste that here. And you could play around with that curve in that Excel sheet as well. I'll put the link in the video description below. So now this curve is part of the parabola that starts at 0, 1 and ends at the point 8, 5. So this is 0, 1 all the way to 8, 5. So x is 8, and 5 is somewhere here, like that. So that's how it would look like. And if you draw arrows of indicating where the particle, if you were representing trying to visualize it as a particle moving across this curve, it would be moving in the arrows indicating it's increasing in time. So again, the arrowhead indicates the direction in which the curve is traced as t increases from 0 to 4. But now in general, the curve with parametric equations, so if we had x equals to a function of time f of t and y equals to a function of time g of t, but now if we restrict t to be less than or equal to b but greater than or equal to a, Yeah, then what they have is an initial point on the curve. An initial point here is defined as at the point f of a and also g of a right here, like that. And then the terminal point, this is what it's often called, is the endpoint of the curve, and this one is at not G, f of B now. So from the initial point of the different point B and G of B, like that. And again, if you were to graph this out like that, this is X, this is Y, you had a random function like this, etc. You could even do something like that just to be general. So we have at this point here, this is at, this value here, this is x is equal to f of b, like that. So this point here is f of b and g of b, like that. And that's at this point across here. That is our g of b. And again, because y is equal to g of t, and x is equal to f of t. And then at this point here, we have the, I'll draw it over across here, we have f of a and g of a, like that. So this is the starting point or the initial point, and this is the terminal point across there. This is, just for completeness sake, this is f of a. Across here, this is g of a, like that. Yeah, so that's just for some terminology. Anyways, that's all for today. Hopefully you learned from this pretty interesting example on parametric curves. And like always, you can download these exact notes in the link below, as well as the Excel notes as well. I'll put that link as well. So stay tuned. Anyways, that's all for today. Hopefully you learned and enjoyed. And thanks for watching. And stay tuned for another Math Easy solution.